We've talked a lot so far about electrostatics and electricity, but now we're going to add something new. Magnetism, it turns out, is closely related to electricity, and we'll spend the next few chapters exploring that connection. The similarities between the magnetic field and the electric field are significant. We're going to use B to represent the magnetic field because it turns out M is actually used for a different kind of magnetic field that we'll discuss briefly, but we won't really use. We can detect a magnetic field by looking at what it does to a moving charge. We know electric fields act on all charges, whether they're moving or not, but magnetic fields only act on moving charges, and the charges have to have a component of their velocity that's perpendicular to the field. So we can write this force as Q V cross B. We know the units for charge, velocity, and force, and we could solve this for units of B, and we get Newton seconds over Coulomb meters, although a much simpler unit is called the Tesla. Again, that's a capital T for the abbreviation because it's a person's name. A magnetic field of 1 Tesla is very strong. The Earth's field is about 50 microtesla. Another common but non-metric unit for magnetic field strength is the Gauss, where 1 Tesla is 10,000 Gauss and the Earth's field is about half a Gauss. The largest fields outside of, for example, the National High Magnetic Field Lab in Tallahassee, places like that, are usually in MRI machines in hospitals and imaging centers, and they're usually a few Tesla. Now, for $10, $20, you can buy a magnet that's about a cubic inch roughly, and it'll have a field strength of about 1 Tesla at its surface. Now, the current world record for magnetic field strength is 1,000 Tesla, but that's something that had to be destroyed to create that field for just a fraction of a second. If you want reusable magnets, the record is about 50 Tesla, so it's kind of interesting when you think that for $10 or $20, you can get to 1/50th of the world record. Of course, over a much, much smaller region than this would be, but anyway. Now, the cross product in that formula tells us the charge has to have a velocity component perpendicular to the field. And we find the direction the way we find all cross products. This is with a right-hand rule, and we're going to see a lot of these in the course. So take the fingers of your right hand, point them in the direction of the charge's velocity, and curl them in the direction of B. When you're done, your thumb points in the direction of the force. Now, a side note here for the engineers, if Q is less than 0, so for example, if we're talking about electrons, that flips the direction of the force by 180 when you're done. Usually electrons are doing the moving, and again, since the engineers don't use our conventional current where we play like it's positive charges, they a lot of times use the left-hand rule. They do everything I described the same, but you use your left hand. We do some examples. Let's say we've got a positive charge here. It's moving down the page, and there's a B field to the right. Take the fingers of your right hand, point them to the floor, then curl them to the right. That leaves your thumb pointing at you, so the force is out of the page, or out of the screen. We do a different one. Here, what if the charge is moving out of the screen towards you? So you point your fingers at yourself. Then you have to curl them up. That means your thumb will be pointing to the left. Every physics book has examples of this, and there's probably a million of them online if you want to see more of them, but you just have to get used to doing this right-hand rule thing. There are other ways you can do it that involve making a little tetrad, a little set of 3 perpendicular axes out of your fingers and thumb. I think that's more confusing than this, but you use whatever you want. If you find something in a physics book that you like better for cross product, that's fine. Now, electric fields start and end on charges, but magnetic field lines don't end, they're loops. And the reason is, it seems there are no magnetic monopoles in nature. A monopole would be an isolated north pole or south pole. Now, we can have electric monopoles, that's positive charges or negative charges, and we've worked with those a lot. There are some theoretical reasons to believe that there may be monopoles somewhere in the universe, magnetic ones. And that would be cool, but that discovery has never been confirmed, so we're going to assume they only come in pairs. This means if you cut a magnet in half, you get another north and another south at that cut, so you end up with 2 shorter magnets rather than an isolated north and south. So we define the field lines to go away from north but not originating on the North Pole, and towards the South Pole, but not terminating there. Now, what if a charged particle moves from a region where B equals 0 to where B is not 0? If we look at this figure here, we look at the right-hand rule. Let's predict the direction of the force when the charge crosses the dotted line. Your fingers go up, then you curl them out of the page, out of the screen, and your fingers should be pointing to the right. So there's a force to the charge's right as it moves. And if you think about it, let's imagine this B field is everywhere. Once it turns on here, let's say it turns on everywhere. What will happen? This thing will be continually pushed to the right. It'll end up moving in a circle. Now, since F is the cross product of V and B, that means it has to be perpendicular to both of them. If the force is always perpendicular to the velocity, that's what gives us the circle. We also know from last semester, though, if something's moving in a circle, there must be a force equal to mv squared over r acting on it. So if we want, we could say the QV cross B, or QVB sine theta, has to equal this mv squared over r. If B and V are perpendicular, as they are here, sine theta is 1, and we can simplify this and solve for r and say that this charge is going to move in a circle with a radius of mv over qb. Now, what's the work that this force does? Well, to figure this out, we can use the fact that work is the dot product of force and displacement. We can write work as the time integral of power, and therefore F dot V integrated over time, that will give us work. We put in what the force is. It's Q V cross B. This is the interesting part. V cross B is by definition perpendicular to both V and B. So V cross B dotted back into V has to be 0. That means we get 0 work. Now, I've put tricky problems on a test before to make you think about this. And here's how we could do it. Let's say I tell you you've got a 2 nanocoulomb charge moving west, 300 meters per second, through a magnetic field 1.75 Tesla, which is up. What's the magnitude and direction of the force? Here you need to know right-hand rule. You should also be able to figure out that the only things perpendicular to both east-west and up-down are north and south. So the answer is either north or south. Point your fingers to the west, where the charge is headed, curl them up into the magnetic field, and your thumb is pointing north. So that's the direction of the force. The magnitude, QVB sine theta, again, sine theta is 1. We put in the numbers and we get essentially 10 to the negative 6 newtons. Now, if I tell you the mass of the particle is 5 times 10 to the negative 8 kilograms, you can very quickly solve for the acceleration. That's not hard. A equals F over m. We get 21 meters per second squared. I could say, what was the kinetic energy at the start of the problem? That's just 1/2 mv squared. That's an easy one. We put in the numbers there. Now, you know that the acceleration is constant, so what's the particle's velocity after 10 seconds, and what's its kinetic energy then? This is the part where I trick people, because I sort of led you into this line of thought. You should be thinking, constant acceleration, I bet I can use kinematic equations. So I could say Vf is Vi plus At, and I plug all that in, and I get 510 meters per second. But that's wrong. Because A is perpendicular to V, the final and initial velocities are the same. It never speeds up. We didn't see this happen with the kinematic equations because we can't have V and A in different directions and still be in one-dimensional motion. They can't be perpendicular to each other because perpendicular doesn't make any sense in one dimension. Now, we could do something else very interesting with this setup. We send in the charge. Let's say we only have, half of the space has the magnetic field and the other half doesn't. So it'll go in, it'll turn around, and it'll get fired right back out, kind of like a reflector for charged particles, only it will have moved over by a distance 2r. If you remember back here, r depends on the mass, the velocity, the charge, and the B field. So, the interesting thing here, in World War II, one of the atomic bombs they were developing required uranium-235. This is less than 1% of naturally occurring uranium, and they needed to enrich it to about 80 to 90%. Most uranium is U-238. You should hopefully remember from chemistry that if they have the same name, uranium, and different numbers here, they're different isotopes. They have 92 protons each, which is what makes them uranium, but one of them has 143 neutrons and the other one has 146. If you want to separate these things, they have 92 protons, they have to have 92 electrons, and all the electrons are in the same places. The only difference is 3 extra neutrons in the nucleus, and chemistry has basically nothing to do with the nucleus. It's only concerned with electrons. So with chemistry, we could do something like separate gold from iron because they have different electron configurations, but we can't separate these two kinds of uranium with chemical methods. So we have to separate them physically. The Manhattan Project, part of what it used was these things. These are crude mass spectrometers because of the way the two different isotopes will behave when they go through. The heavier isotope makes a wider circle, so when you fire them both in, you ionize them and fire them into this magnetic field. The stuff you want, the uranium-235, makes a shorter, tighter circle, and the heavy stuff is out here. So if you put a tiny little thing here to catch it, like a bucket, only of course much smaller, here you'll catch U-235, over here you'll catch U-238. This would be called depleted uranium, and this would be enriched, the good stuff. These things were called calutrons because they were designed at Caltech, I believe. But one of the reasons this was such a big deal is you're separating this stuff at the atomic level. It's going to take a really long time to get a few kilograms of uranium-235. There's not any particular technical difficulty involved in making a bomb if you have the U-235. You essentially make a cannon, and you have a shell and a target, and they're both subcritical masses. There's plenty of information about doing this on the internet, in books. It's not classified. The hard part is getting the uranium-235. And when a country starts doing this or is suspected of doing this, the other nuclear powers in the world usually work together to stop it because they don't want anybody else having nuclear weapons. Now, instead of single charges, it's a lot more common to deal with currents, with many charges. How would we calculate the force on a current-carrying wire in a magnetic field? Well, we use the fact that a current I multiplied by a length of wire dl will give us something equivalent to a charge dq multiplied by a velocity v. We integrate that, and we get F is I L cross B, or ILB sine theta. We get the direction from the same right-hand rule as before. The fingers of your right hand point in the direction of the conventional current, and you curl them into the direction of B. Your thumb then points in the direction of F. If we look at what happens to a current loop in a magnetic field, we get some sort of interesting results. So imagine we have this battery. We've got a current going around like this. All these currents, of course, are the same size since this is a series circuit. But anyway, the magnetic field is the green stuff, and we look at the forces. Now, I3 and I1 and I5, they're either parallel to or anti-parallel to the magnetic field, so we know there won't be any force there. We'll have sine of 0 or sine of 180, and those go away. These are the parts that matter, the left and right side. Here, if we use the right-hand rule, we go up with the fingers of your right hand, curl them to the right, your thumb is pointing into the page. On the other hand, if we point down, curl our fingers to the right, your thumb is pointing towards you. So, because this field is uniform, we get the same value for F2 that we do for F4. What that means is there's not going to be any movement of the center of mass. We have two equal and oppositely directed forces. But since those don't go through the center of mass, they cause two torques, and those torques happen to add. They combine with each other. If we say the center of the loop is our origin and we measure out here and say, the whole thing is W wide and this is W over 2, this half of it, torque from last semester was R cross F, so that would be W over 2 is our distance. And then our F is ILB sine theta, and then we've got the sine of the angle between R and F. Now, I2 and I4, they're vertical, the magnetic field is horizontal. The loop might spin. However it spins, though, theta the angle between I and B, is always going to be 90. So if you imagine this loop spinning around along this axis, this is always up, this is always down, and this is always left to right. So they'll always be perpendicular. This will always be 90, so we can get rid of that sign. Now, the two torques are both trying to rotate the loop the same way, so they add. So our total torque is then 2W over 2 ILB sine phi. Phi is now the angle between our lever arm, W over 2, and the force. This doesn't stay 90. This is 90 as it's shown, but as the loop rotates, the left side falls into the screen and the right side comes out. And that's backwards to what I have here. It will go to 0. The torque will disappear when the loop is rotated, so that I2 is as far below the page as it can get, and I4 is as far above the page as it can get. Then we'd have 0 torque because our phi would be 0. Now, if we want, we could write that instead of IWLB sine phi, W times L is the area. So we could say it's IAB sine phi. Now, instead of one loop, what if we wind many loops of wire around this? If we do that, each loop we wind, we get another factor of the torque. So we could write this as N, for N loops, IAB sine phi. Now, this looks like this is very similar to the expression for the torque on an electric dipole. So we're going to define a magnetic dipole moment as mu equals NIA, and now we can write T is mu cross B. Once the loop rotates 90 degrees, this is what we're going to see. Imagine you're over here now in the plane of the paper and looking to the left. What do you see once it's rotated? Well, you see I4 up, I2 down, right? I4, this side comes up, this side goes down, right? Up and down. And if you look at the forces now, all the forces are trying to pull the loop apart rather than rotate it. All the sides are pushed outward. This current carrying loop acts like a bar magnet where the field points out of the page up here. Or rather, the field points into the page for this bar magnet. I'm sorry. That needs to be corrected here also. Now we go back to our first picture. What would this look like in terms of bar magnets? Well, the green lines would look like this. We know that the field leaves, it's directed away from the North Poles. This thing is going to look like a magnetic field directed into the page. So south is the part we see. If you've ever played with magnets before, you probably did this. You bring them together, and if you hold this one still and let this one pivot, it'll spin around so that they line up. That's exactly what happens here, right? That's what's happening. Once we do this, the fields will line up. Now, there's something that's even neater about this. What if instead of just the simple circuit we had before, let's say our circuit looks like this. We have this wire that almost makes a complete loop, but it touches these C-shaped things that are connected to the battery. So that's how it gets its power. It's going to try and rotate 90 degrees, just like we showed before, but when it gets to that point, it will break the connection here with the circuit. There won't be any more current going through this. So it'll spin up, and then the circuit breaks, but the angular momentum from the spin up is going to keep it going, and it will go across this gap. It's going to be connected to the battery again, only now the current will be going the other direction. And if you go through this carefully, you'll see that it is again going to be forced to flip around one more time. And when it goes vertical like this, again the circuit breaks, the angular momentum carries it, the circuit reverses, it keeps spinning the same way over and over and over again. This is a simple motor. These things are called brushes and commutators. Now, we have something now that will turn electrical energy into mechanical energy, so that's kind of a big deal. Our last topic for this chapter is the Hall effect. This is the experiment that originally showed that currents in solids are carried by negative rather than positive charges. Now, for everything we've done so far, it doesn't matter if we consider a current of, say, positive charges moving to the right or negative charges moving to the left. We get the same answers. Of course, we know now, because of the atomic theory, that the electrons are really doing the moving, not the nucleus. We should confirm it with an experiment, though. So let's say we have a simple loop of wire, only here we have a very wide flat wire, like say we connected ordinary wire to a cookie sheet, this big wide metal plate that's flat. We have a magnetic field going directly into it. Now, if I look at the battery's orientation, our conventional current, so the way physicists do things, we would say positive charges leave here, they go around clockwise. Now, when they go through this magnetic field, do the right-hand rule. Point your fingers down, because that's the way it's moving. Curl your fingers into the board or the page, and your thumb points this way. So some of them are pushed off to the side like this. Now, when they're pushed off to the side, these things have their own electric field, right? And when enough of them accumulate here, and it doesn't take many, their electric field acting on the next positive charges through will be enough to counteract this magnetic force, and these positive charges will just go right on through undisturbed. But it's because there are positive charges that will be lining this side to counteract that magnetic field. So we say, okay, this is what happens for positive charges moving. What if it's negative charges that do the moving? They would leave from the bottom and go counterclockwise. When they get up here, if you do the right-hand rule, you point your fingers this way, curl them into the board, you get something pointing this way, but then you remember, oh, these are negative charges, they go over here. So they would line this side, and they would create an electric field which would cancel out the magnetic field for later negative charges that would just go right on through. So what we notice here is the sign of the charge carriers. If it's negative, then the right side will be more negative in voltage than the left. If it's positive, the right side will be more positive in voltage than the left. So we can do this one experiment and figure out what is this, what's the sign of the charge carriers. All we need is a voltmeter here. Now, you might think, okay, they did this experiment and then, to be good scientists, a few other people confirmed it, and now we know that, yeah, negative charges are carrying the current, so we can be done with this, put it in a museum. It turns out this is a really easy way to detect magnetic fields without having to have a magnet in the neighborhood, which is kind of nice. Their chips that can do this are called Hall effect chips. They're very cheap. These things are in the ballpark of $1 or $2 each. And they can be even smaller than these things. These are much smaller than a penny. I've got a line of them here being tested for something. They only have 3 terminals. There's power, they take 5 volts usually, ground, and then the signal out. If you connect a voltmeter between ground and the signal, you can just watch the voltage change depending on which way the magnetic field is going in direction and strength. These things are in a lot of consumer products, including things like the old flip phones and iPads, where if you've got a cover for it, a magnet in the cover tells the iPad whether it's open or closed. They can be used to count the teeth in a gear when they move past a Hall effect sensor, and you can see how much a motor has rotated or if it's moved at all. So these are very useful, and they're all over the place, and they rely on the Hall effect.